So, the mole. The time has come. If you're a chemist, it is one of the most useful terms in the entire chemical vernacular. And it's a very simple concept, really. We Americans and British tend to refer to what's called a dozen of something regularly. And a dozen is nothing more than a word that takes the place of a number. And a dozen of something means 12 of something. So that's essentially what the mole is. It's a number of things. The only difference is a mole represents a very large number of things. This is the number that's equal to a mole of something. It's extremely large. This is a big number. If those are my millions, billions, trillions, quadrillions, pentillions, we're up into hexillions. You've got 6.022 times 10 to the 23rd of something, otherwise known as Avogadro's number. Now, a mole also represents something else besides a large number of things. It also represents the mass in grams of the formula of whatever you're talking about. Now, that may not seem obvious at first, so let me give you an example. I'm going to pick and only talk about elements in this video. We'll talk about compounds later. But if I randomly chose the element silicon, and I said that I have a mole of silicon, now, that's really not a lot of silicon. It's a fairly small sample, believe it or not. Sure, 1 mole of silicon equals a huge number of silicon atoms. Silicon atoms. You may offhandedly say I have a mole of silicon, but what you're really saying is you also have 6.02 times 10 to the 23rd atoms of silicon. But you also have the formula mass of silicon in grams. Now, what does that mean? Well, this formula is just an atomic symbol. So I'd look up the atomic mass for the formula mass of silicon. And if you look at the periodic table and round off to the nearest tenth for simplicity, silicon's atomic mass is 28.1 atomic mass units. So the gram atomic mass of silicon is 28.1 grams. So, if I were to hand you a mole of silicon, yes, it would be the same as handing you Avogadro's number of atoms of silicon, but it would also be as if I handed you 28.1 grams of silicon. And that's not a lot of silicon. That's only a fraction of a kilogram, much less than a pound. And the same is true of any element. Randomly pick iron. Well, if I were to hand you a mole of iron, yes, I'd be handing you this many atoms of iron. And I would also be handing you the formula mass in grams of iron. And since iron's atomic mass is 55.8, if I handed you a mole of iron, I'd be handing you 55.8 grams of iron. And at this point, you may be saying, oh, isn't that nice that all these things are equal? So what? What does that do for me? How do I use it? Well, I like to refer to this as the Holy Trinity of chemistry, because these three things allow you to do a large number of calculations involving matter. And as an example of how we can use them, we've already learned how to use equalities as conversion factors. For instance, if 1 meter equals 100 centimeters, I can create a conversion factor out of this relationship. And this ratio, which is this equality, lets me convert between meters and centimeters or centimeters and meters, depending on how I write the ratio, inverted or as written here. Now, the same is absolutely true of these three things that are true in my Holy Trinity. Namely, I can create ratios for conversion. For instance, I could write that 1 mole of iron being equivalent to 6.02 times 10 to the 23rd atoms of iron, I can use this as a conversion factor to convert atoms of iron in a sample to how many moles it is, or how many moles to atoms of iron. I can use instead this relationship, the fact that there are 55.8 grams of iron per every 1 mole of iron. I can use this ratio to convert between moles of iron and mass of iron, or vice versa, mass of iron to moles of iron. By the way, this particular ratio from the Trinity that involves mass and moles is called the molar mass. You don't really need to know that to use it, but it's a nice fact to know. There's another ratio I could create from this Holy Trinity, namely a ratio of atoms to mass. I can say there are 6.02 times 10 to the 23rd iron atoms equal to 55.8 grams of iron. And this ratio of the three possibilities would let me convert a mass of iron to atoms of iron, or atoms of iron back to mass of iron. So I would use whichever two of the three as a ratio for whatever conversion I was trying to achieve. And now for some examples. So now, what if I in fact had this kind of problem? In a 45-gram sample of lead, how many atoms are there, and how many moles does this sample represent? Well, what I strongly recommend you do until you get used to quickly and easily making these conversions is write out the Holy Trinity for the substance involved. And if I look at my periodic table, I know lead is atomic number 82. Therefore, I can write 1 mole of lead, Pb the symbol, equals Avogadro's number of lead atoms. And it also equals the gram formula mass of lead. And since lead's atomic mass is 207.2 atomic mass units, its gram formula mass is 207.2 grams of lead. Now I can create a conversion factor out of any two of these things in a ratio. And then I go to my problem, and we follow a problem-solving technique where we like to start with the answer. And this question is asking me for a number of atoms of lead. So I am going to use this as the numerator of my starting ratio. I have this many atoms of lead. Anytime I have a sample of lead, per, now what's this per? Well, it's either per a mole of lead or per 207.2 grams of lead. And in this case, because I was given a mass, I use the mass as the other part of my ratio. Namely, if this equals that, then yes, Avogadro's number of atoms are equal to 207.2 grams of lead. And I chose this to get my answer, atoms of lead, because I have a mass of lead that lets me cancel this mass of lead by multiplication. If I multiply by 45 grams of lead, which I have in the sample, mass of lead cancels, and I'm left with atoms of lead, my answer. You grab your calculator, you divide 6.02 times 10 to the 23rd by 207.2, and you multiply by 45. Avogadro's number is a measured number with 3 digits. Atomic masses are measured numbers, 4 digits, and 3 digits for the mass of the sample that I measured. I want 3 digits in my answer. 1.31 times 10 to the 23rd lead atoms is the answer. And yes, it's a very large number of atoms. For part 2 of the problem, again, I like to start with the answer. It says how many moles are there in the sample. And when I look at my trinity up here, I see moles right there. There's how I want to start the problem, with 1 mole of lead per one of these two things that it's equal to. And once again, since I have a mass of lead with which I could cancel a mass of lead were it down here, I'm going to use the mole to mass ratio. 207.2 grams of lead are what a mole of lead equals. So then when I simply multiply by the mass of lead given in the problem, Mass of lead cancels, leaving me with my answer, moles of lead. I divide 45 by 207.2, and with a 3-digit and 4-digit number, I have a 3-digit answer, 0.217 moles of lead. So yes, even with a 45-gram sample, I don't have that many moles of lead. It's only a fraction of a mole. That's how big a mole is. And a couple more examples now. Given 4.20 times 10 to the 24th atoms of krypton, a very large number of krypton atoms, what mass of krypton is this, and how many moles does this represent? Once again, I recommend writing your trinity first. That being, in this case, 1 mole of krypton, symbol Kr, always equals Avogadro's number of whatever you're talking about, and these are atoms, so it's atoms of krypton. And it always equals the formula mass in grams of what you're talking about. And since this is just an atomic formula, I look up the atomic mass, and the atomic mass for krypton is 83.8. And so the gram formula mass of krypton is 83.8 grams of krypton. Now, if I want to find mass of krypton, and this is a mass of krypton, I'm going to start with this in the numerator of my ratio. And yes, there are 83.8 grams of krypton per 1 mole of krypton or that many atoms of krypton. Now, because I was given atoms of krypton in the problem, I'm going to use this for my ratio denominator. 6.02 times 10 to the 23rd atoms of krypton. Because if I want the mass of krypton, all I need to do is cancel the number of atoms of krypton, which I was given in the problem. Therefore, a one-step multiplication, atoms of krypton, and my atoms of krypton cancel, and I am left with the mass of krypton. And in this case, my 3-digit answer would be 583 grams of krypton, about half a kilogram. In the second part of the problem, again, I like to start with the answer. And since the question requests moles, and there is a mole of krypton, I'm going to use that as the numerator to start my conversion. And in the denominator, once again, I either have to set it equal to that many atoms or that mass. But once again, because I'm given atoms, I'm going to write the ratio that 1 mole is equivalent to Avogadro's number of krypton atoms. Because then, given that I have 4.20 times 10 to the 24th krypton atoms, in one step, the atoms cancel, and I have my answer, moles of krypton. And my 3-digit answer in this case is 6.98 moles of krypton. And for a last example, one of the problems I love to ask, and people seem to love to mess it up every year, is I ask, what is the mass in grams of 15 carbon atoms? Now, of course, a gram is a fairly large mass unit, and atoms are imperceptibly small, so 15 of them should have an extremely tiny mass. So I can check my answer by making sure it's pretty small. But I'm still going to do the same thing. I've changed the substance I'm talking about, so I'm going to write the trinity. 1 mole of carbon is equal to Avogadro's number of carbon atoms, and it is also equal to the gram formula mass of carbon. And carbon's atomic mass is 12.0, and so the gram atomic mass is 12.0 grams of carbon. Then I go about doing the problem. I'm asked for a mass in grams. There it is. There's my starting point, 12.0 grams of carbon. But I can't write it all by itself. It has to be paired up with something else in this equivalency. And of course, because I gave a number of atoms, I'm going to pair it up with the number of atoms that are equal to the gram formula mass. And that's Avogadro's number of atoms of carbon.